All right, everybody, lecture 5. Let's get started. Let me just add a little bit. That's better. I'm hoping that homework 2.1 was pretty straightforward. Good. So, really, it's just meant to just make sure you were paying attention in class on Wednesday, but also just sort of stretching it a little bit, maybe at least with that second problem, that you understand that, you got different bolts going through different components of the cross-section, all that. Okay, so we're going to jump right into today's topic, which is we're going to address how to compute net area for a staggered bolt arrangement. What we're going to find is that it's not really difficult, but at least from a computational perspective, the problem does sort of get longer all of a sudden. And so we'll talk. You'll see what I mean when we chip away at this. Okay, everybody get the code? All right. So let's just sort of recap where we left off from last time, and I think this slide really summarizes our net area expression so far. In that, right now, what we've got is a net area expression where we take the gross area, we just subtract the area loss due to the presence of bolts, which is the sum of the diameters times the thickness. As for the thickness, it's, I say plate thickness, but it's really the thickness of whatever the bolt is going through. So it could be a flange, a web, whatever, As for the diameter, we are using an effective hole diameter, which is taking the bolt diameter and adding 1/8 of an inch. Now remember, the reason that we add 1/8 of an inch is because we're adding a 1/16 twice, right? We're adding 1/16 of an inch to account for the fact that the bolt, the hole is actually physically larger than the bolt diameter, and then we add another 1/16 of an inch to account for that damaged material right around the hole drilling and whatnot. Let's see. Okay, so the problem with that formula is this, is that if we ever have a staggered bolt arrangement, that formula doesn't work, okay? And so just to sort of give you kind of a view into what's going to go on here, okay, so let's do like a really simple problem. So let's say that here's a member and I'm yanking on it, and I'm going to try and compute the net area. And what I'm going to do is I'm going to say, okay, let's just say it has 2 bolt holes. Let's just say it has 2, okay? And let's say I want to determine the failure along this path, okay? In other words, like if I yank on this, that the member fractures along that path, okay? Now, if I were to compare that against, let's say, 2 holes like this, right, and I'm yanking it like that, and I'm failing like this, would everybody agree that the area here, or that length of that failure path, is going to be larger than this one? Would everybody agree with that? Okay, so here's what I propose, is that this net area right here is going to be the gross area minus 2 bolt holes. Everybody, like, that would be pretty straightforward. This one is going to be the gross area minus 2 bolt holes. But then what we're going to add is we're going to add something called a stagger factor. Okay, bless you. And we're going to add a stagger factor for every diagonal path that is present along the bolted connection. Okay, so for example, if we were looking at this image down here and we had, like that, and that, we would add a total of 4 stagger factors, because we've got 1, 2, 3, 4. Okay, and so I'll go through here in a bit what a stagger factor is. But the idea that I at least want to convey here is that the difference between this and this is that we are adding a stagger factor, because the difference between this and this is that the net area is getting bigger, right? We are increasing the net area. And in fact, that's the whole point of staggering bolt arrangements in general, is that the reason that we take the bolts and that we arrange them in this staggered fashion is to increase the net area. And if we increase the net area, we increase the strength. If we increase the strength, maybe we can use a smaller member to withstand the same amount of load, which will save us money. Okay? That's sort of the point of doing this in the first place. All right, so one of the things that I have sort of mentioned a little bit, but now we kind of need to be a little bit more rigorous about, is that whenever we're dealing with staggered bolt arrangements, here's the two problems that we're going to have to address. The first address is how do we account for the increased area along the diagonal failure paths, and the answer to that is we're going to use stagger factors. The other is how do we account for multiple failure paths. And I guess the point I want to mention is that there are indeed multiple possible paths upon which a staggered bolt arrangement could fail. Okay? Now, first off, before we get into identifying these, we should recognize that we only investigate failure paths that occur along the lead line of bolts. And so I have this bolted connection configuration, and I'm highlighting in yellow the bolts that I'm considering along the lead line. And if you want a really easy way of identifying the lead line, imagine standing at one end of the tension member and just shining a flashlight. Any bolt that hits light is going to be one that that is along the lead line. So notice how I'm not highlighting, like this one, because this bolt's in front. Okay? Here's sort of the idea. Okay? Imagine that this tension member was like a really long sheet of paper. Okay? And let's say that let's say I'm only stapling one side of the sheet of paper to the wall. And let's say that, here's the sheet of paper, and everywhere that there's a bolt, I staple the paper to the wall, okay? And then I'm grabbing the piece of paper and I'm yanking on it. And I'm asking you, how can I tear the paper in half without ripping through one of the staples? And the only way to do that is if it fails sort of along this path here. Does that make sense? Because if I were to rip the paper like this and the paper were to separate, I'd have to yank these staples out of the wall. Does that make sense? Now, the answer, or a natural question to that could be, well, wait, are you saying that the staples couldn't fail? No, I'm not saying that at all. And analogous to here, I'm not saying that the bolts couldn't fail either. It's entirely possible that in the space of the bolted connection, the tension member is fine, and it's the bolts that fail. And we'll talk about that later. After tension members, we're going to discuss how do we analyze the design bolted connection. So we'll get to that. So for now, we're just considering, bless you, for now we're just considering the tension member itself and figuring out the ways that the tension member can fail. Everybody with me on that? Okay. So here's what I mean when I say identifying all possible bolt failure paths. Okay? So let's consider this connection, okay? And by the way, the main body of the member, the gross section of the member, is all the way over here to the right, okay? So what I'm going to say is that bolts C, D, and E, those are the bolts that are on the lead line, okay? Now, what we're going to try and do is identify all of the potential failure paths that this tension member could experience that would cause the tension member to fracture in half. Okay. Now I'm going to walk you through the first one, and you'll just bear with me on this one. Then I'm going to ask for your help on some others. So one potential failure path would be BDG. In other words, just right like that, right through those bolts. Okay. Now think about what's going on here. Okay. So imagine this is sort of like like a piece of paper, piece of taffy. I'm taking it, I'm yanking on it. Okay. I'm yanking on it like this. So the member's natural instinct in terms of wanting to fail is that, if I'm yanking it like this, it's going to want to fail like that, right? It's not really going to want to fail at an angle. Okay. The only ways that it would fail at an angle is if it's between bolt holes. In other words, like, I really wouldn't have a failure path that looks like that. Like, that doesn't really make sense, right? Because that's going to be a much larger area than this. think that failure path is going to be the smallest area, right? So the first point I want to mention is that the only time that there's a diagonal path is between bolt holes. Everything else is going to be perpendicular to the axis of the member. Does that make sense? Okay, if that makes sense, I want somebody to give me another potential failure path for this member. Somebody in here. A, C, A, C, E, F. Okay. I'm going to say, okay, so I see what you're saying. You're saying go like this, right? Okay. I'm not going to do that one because I'm going to say that in order to tear the paper off the wall, we'd have to rip through that staple. So I'm not going to use that one, okay? So it's got to wrap around the lead line, okay? So let's try another one. A, C, D, E, F. A, C, D, E, F. That's another one. That's one, too. In other words, the member rips like that. That is one. There are more, by the way. There's more.
A, C, D, G.
A, C, D, G. There you go. Can anybody identify another one?
B, C, D, E, G.
Well, okay, this right here. Okay, so let's talk about that one. Okay, so you're saying B, C, D, E, G, right? Okay, so you're saying that. Here's my question about that. So let's talk about this failure path. If you were yanking on this, would it fail like that, or would it just fail like this? It would just go EF. So instead of B, C, D, E, G, it would just be that. I'm saying anything that's not between a bolt, a series of bolts is going to be perpendicular. Okay? I want to go back to this third path. Does anybody see an analogy to that third path?
B, D, E, F.
B, D, E, F. B, D, E, F. Again, anything perpendicular to the axis of the member, the only diagonals between the bolt holes. Does that make sense? Now, here's the other thing. I'm going to stick this one with this one, okay? And I'm going to tell you why. And I'm doing that because I'm assuming that the member is symmetric, okay? Let's see if I can quantify that a little bit. Let's see if I can quantify that a little bit. Okay. Let me ask you this. Let's start with this first path, this BDG. How many bolt holes would I need to subtract for path BDG? 1. How many staggered diagonal paths are along BDG? 0. How about ACDEF? How many holes am I going to subtract? 3. And how many diagonal paths are there? 2. Okay. So, okay, if you understand that, maybe you'll also understand why I'm grouping these together. Okay? Let's take path ACDG. Let's take the first one, ACDG. How many holes? How many diagonal paths? Okay, what about BDEF? How many holes? How many staggers? 1. So, assuming that the member is symmetric, okay, in other words, that the dimensions of this diagonal path are the same as this one, am I going to get a different net area here than I am here? No, they're going to be the same, which is why I'm lumping them together. If this dimension was different than this one, then they would truly be different net areas, which, I'll say this, in most instances, we would never do that in the real world. There are a couple of cases where you might see that, like if you have stagger across an angle leg, but for the most part, if you're just looking at a simple connection like this, you're going to do everything symmetric. Does that make sense? Everybody good with that? Okay. Now, the big thing is what's going on with these stagger factors, okay? So for every one of these diagonal failure paths, what we're going to do is we're going to add a stagger factor, and the way that we compute that stagger factor is the following. This is S squared T over 4G, okay? Now, the way that we define S and G is, so if we're looking at, let's say, this diagonal path right here, S is the dimension that is parallel to the load, which, in other words, S is the dimension that goes that way, and G is the dimension that's perpendicular to the load, so it goes that way, okay? Now, some of you might be thinking, like, well, why don't we just, like, do some trig and get the actual just area along that plane? Well, this is going to make sense a little bit later when we look at shear lag, but all I'll say about that for now is that the stresses that you actually see in bolted connections, like if you were to run a detailed finite element analysis, the stresses are pretty complicated, and what we're looking at here is an empirical expression that sort of captures the effective increase in net area, and it does so in a pretty simple fashion, so you do lose a little bit of accuracy, but it's really, really easy to use, okay? So, one thing I will mention, by the way, is that if some of you are astute enough to open the manual and find this section, some of you are probably going to get a little upset at me because the manual does not say S squared T over 4G. The manual says S squared over 4G. And some of you are going to go, wait, Dr. Mike, where'd the T come from? Because that says S squared over 4G, and you threw a T in there. Well, if you read the manual, what the manual says is you add a stagger factor for each diagonal path. Okay, so if you think about this from a units perspective, S squared over 4G, S squared over 4G is going to have units of inches. Okay, but you still need to multiply it by the thickness to get an area. Remember, we're adding and subtracting areas. So I'm throwing the thickness in there because you're going to have to throw that in there anyways. Okay? Now, one thing I do want to clarify, let's say you have a connection like this, okay, and you're wanting to investigate this failure path, okay? So if you're wanting to do that, what you do not do is say, oh, this is S and that dimension is G, and come up with one big old stagger factor for the whole thing. You don't do that, okay? Instead, what you do is you have a stagger factor for this path, for this path, for this path, for this path. So instead of one really big stagger factor, you use 4 really tiny stagger factors. Because the math doesn't work out that way. You're taking S squared over 4G, so you can't just lump it all into one big S and get the same numerical quantity. The math doesn't work out that way. So you do need to treat each diagonal path separately. Okay? Is everybody okay with that? So just keep that in the back of your head. So now I have a more complete expression for net area. So now I propose that my real net area expression is going to be that the gross area equals the net area equals the gross area minus the area loss due to the presence of bolt holes plus any necessary stagger factors. Okay? Now, there's actually a lot more baked onto the slide right here because I say this is our expression for net areas of bolted connections. And one of the things I didn't talk about is what about the net area for welded connections? Well, for most welded connections, the net area equals the gross area because you're not removing any plate material in most cases to generate a welded connection. It's like the most common welded connection is a fillet weld, like slap an angle on a plate and just weld around it. You're not drilling. You're not creating any holes. So the net area and the gross area are just the same. So that's why I wanted to throw that here. So yeah, a fairly contained slide that contains everything we need for a complete expression of net area. Everybody good with this? All right, let's get to work then. Okay, I want to compute the net area for this plate. Let me get to the notebook here. I don't know why all these pens show up in OneNote. It sort of bugs me. Okay, so we're going to compute the net area for this plate. The plate is 1 inch thick. One thing I do want to mention, let's see, is this term right here. We're going to see this a lot throughout the semester, this TYP. That just stands for typical, and I'm basically It's so that you don't have to keep repeating the same note over and over and over and over again. So we'll just use 1 1/2 inches to represent this dimension. Okay? So this is our break line and this is our tension member. So basically what that means is that we are taking the tension member and yanking on it this way. I can draw an arrow better than that. Let me do better than that. So we're yanking on it this way. So we do kind of need to know that so we know which dimensions are parallel to the applied load and which dimensions are perpendicular to the applied load. Okay. And we do now have a more complete expression. So this is going to be our net area expression. And we have our stagger factor right there. So just so we have something to go off of when we start performing our calculations. Okay, so if we need to compute the net area, can somebody tell me a necessary first step? Finding the gross area, okay? So let's see if we can throw some dimensions on here. So what is this dimension right there? Like the whole length. So we have 2.5, 3.5, 3.5, 2.5. So let's see, 2.5, 3.5, 6, 6 times 2 is 12, right? So we'll do 12 inches. So I think I can do that one in my head, that we can say that the gross area is just 12 times 1, which is 12 square inches. Okay. All right, so let's just sort of go to our expression up here, and let's see what values in our expression can we just sort of figure out. We do know that the thickness is 1 inch. Okay. What about the effective hole diameter? There we go. That's going to be 7/8 of an inch. Okay. All right. What about our stagger factor? Okay, so let's do the stagger factor calculation over here. All right, let's move that over. All right, so somebody help me out. If we're looking at a representative diagonal path, what is S? 1.5 inches. Why is it not 3.5 inches?
S is parallel to the load.
There you go. So this is 1.5 inches. This is 3.5 inches. Does that make sense? Everybody okay with that? So, therefore, let's do this. Would you agree that we can just do this and maybe get just 0.875 square inches, just 7/8, right? For our stagger factor, so that's going to be S squared T over 4G, okay? So that's going to be 1.5 inches squared. Times 1 over 4 times 3.5. So what does that come out to be? And let's do 3 decimal places. And by the way, a lot of times in class, I'll probably do the calculations to 3 decimal places just so that we can all follow where the values are coming from, although maybe if I was doing this in practice, 2 decimal places would probably be just fine, so. So what do we have for this? 0.161. Do I have a second on that?
Yep.
And notice how the units are square inches, because we have inches to the third on the top divided by inches, or the inches cancel and you got square inches, however you want to look at it. Okay. All right, is everybody good on that? Okay, so let me ask you a question. Which is the lead line? The bolts here over here on the left, or the ones over here on the right? The left, right? Because the main body of the member's over here, so this is where you shine the flashlight. So my lead line is basically going to involve that bolt, that bolt, that bolt, right? That's my lead line, okay? So let's come up with some naming. Let's see. Let's do... Just do that. Somebody identify a failure path for me. And let's do this. We'll do it right here. Let's do viable paths. Somebody give me one. ADF. Okay. Does everybody agree that's a viable path? Okay. 2. Give me another one. BCDF. Everybody agree that's a viable one? How about another one? Say it again. Is that going to be the same thing as BCDF? Yes, it is. So I'm going to lump these together. How about path number 3? Okay. Okay. So that I don't have to keep scrolling and whatnot, let me just write these here on the board. Okay, so these are going to, or BCD. Okay, so that I don't have to scroll too much, I'm just going to put this here on the board and then I'll translate it here on the notes here a bit. I'll put this in the notebook here in a second. How many holes are going to be along path ADF?
1.
How many stagger factors? How many holes?
2.
How many stagger factors?
1. 3. 2.
2. Okay. All right. So let's. I'm an engineer. I like tables. Let's do this in a table. And then we have. I think it was BCDF. Is that what it was?
Yeah.
And then okay. All right. So our so we'll say number of holes. And then number of stagger factors, right? Okay. Now how about for each of these paths, we're going to have a net area. So how are we going to get the net area for the first path? Well, the net area for the first path is going to be, well, how do we compute net area? Remind me.
The gross minus the area left holes.
Plus
Plus the stagger factor.
plus the stagger factor. So what's our gross area again? minus how many holes? Right? Okay, let's just write down the formulas for the remainder. So this is going to be 12 minus 2. But for this path, we're going to have to add. Here, we'll do it like this so we can follow. And then the same thing here. All right, does that make sense? So I think what I'm getting at is what we have done is identified viable paths. For each one of these paths, what I want to do is compute, if it were to fail along this path, what is the area? So if it were to fail along path 1, what is the area? I'm asking. So if it were to fail along path ADF, what is the area?
11.125.
11.125. All right. What about the second path?
10.411.
And how about the third one?
9.697.
Okay. First off, do I have seconds on all this? Okay. Now, I'm being facetious, but remind me, what was the question again? What are we trying to do in this problem? Like, what are we trying to do in general? Compute the net area. I don't have one net area. I have 3. So now what? Let me ask you a question. Can somebody look at these net areas? Like, let's ask it this way. If you were calculating the strength of this member, and you had to choose one of these values, which one would you choose?
Smallest.
Why would you choose the smallest?
Safety.
Safety. That's a good answer. Another way of saying it is, if I yank on this, it's going to fail along the path of least resistance. And how could we define the path of least resistance? Well, for a steel tension member, it is the minimum area provided to resist load. In this case, this one. So I ask you, what is the net area of this member? The net area is 9.7 square inches. And that's the answer. Does that make sense? Okay. Is that challenging? You tell me. That should be pretty straightforward, right? Okay. I'm glad you said that, because I do have a fun one for you this weekend. I'm going to show you the fun one. So this is the problem I've given you this weekend. A lot more. I'm going to say a couple things about this problem. I threw a few more bolts in there. But what I don't really think the number of bolts is what makes the problem quote-unquote challenging. What makes the problem challenging is when you look at this path and this path, you have different factors, okay? So I'm not kidding when I'm saying there are quite a few potential failure paths for this member, okay? And so the challenge is going to be identifying them. The math is actually going to be pretty repetitive. And by the way, is there a program that you think might make the calculation a lot easier? There you go. I don't care if you throw an Excel calc in in your submission. I don't care about that. You're engineers. By the way, we are going to have, so I've done some things differently this semester, and so when we start doing tension member design, I'm gonna have one assignment devoted to using Excel to select tension members. So that's something I haven't done before in here. So I might as well just get comfortable with it. So if you all want to use Excel to make the math a little easier, that's fine. The 14 by 1.5 inch plate, and yeah, I kind of came up with this one just in my noggin. So sound good? Okay. I do want to talk a little bit about what's coming on Monday, but then I'm going to let you go a little early. But any questions on this stuff so far? Okay. So let's just sort of set the stage for where we're headed. And I told you that really this is our goal for this semester, to ensure that our resistance is greater than or equal to our loads. I know I've got one person in here that's had a course in concrete design before, and they'll tell you that's really kind of the goal in any structural engineering design exercise, is to ensure that your factored resistances are greater than or equal to your factored loads. And we're not there yet. We haven't really been talking about that yet. So let's just sort of like big picture this whole thing. So here's our factored loads and resistances. When we're looking at tension members, we're looking at gross and net sections, okay? If you recall, when we looked at the spec, we had defined, like, what were the limit states we were going to look at and how we were going to compute the capacity. So maybe what we can do is just sort of distill that and say that we're going to have two limit states we're going to evaluate: gross section yielding and net section fracture. So let's just take a look at gross section yielding. How would we compute the axial tensile capacity of a member according to gross section yielding? Well, we would take the yield stress times the gross area, multiply it by 0.9. Do we all know how to compute the gross area? Yeah. Do we know how to look up the yield stress? If I give you that it's A572 grade 50 steel. Yes, we've done that before, right? That was what homework 1.2 was all about, right? So we've already done this. Okay, what about this one? 0.75, well, I know how to use that. FU, the ultimate tensile stress. I can look that up. The net area, well, now that's not a mystery. We know how to do the net area. So what haven't we talked about? This U thing, whatever this is. And by the way, these are two limit states. We're going to add a nifty one later called block shear rupture. That'll be a little later, but we're going to add that one as a third one on our list later. So what is shear lag? Okay, so I'm going to talk a little bit about what shear lag is and how we handle it. I know we talked about this last semester, but if I were to throw the term finite element analysis out there, y'all probably heard that before in some other classes. Essentially, a finite element analysis is a computer-based or a numerical-based means of performing advanced structural analysis. And the thing is, as I told you, the stresses around connections are really kind of weird. That's the best way of putting it. So what you see here on the right, these are some finite element simulations that sort of show you what the stress contours look like when you take a piece of steel and you load it. And in the real world, we have connection regions that disturb the stresses, right? So if you look in the gross section, so what we see here is this stress contour, and so anytime that the colors are uniform, like out here in the gross area, we see a uniform stress, okay? So out in the gross area, we have uniform stresses, okay? But not here, not in the net section. So this is the net section. Remember the net section's right here? Here the stresses are all over the place, okay? We have a lot of discontinuous stresses and non-uniform stresses that are near the connection. And what that does is it results in a reduction in efficiency of the member. Because the stresses are not uniform, we cannot assume that all of the member can reach the same stress, right? So, like the idea is in the gross section, the stresses are uniform. Yank, 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 yank. And when we hit Fy here, we hit Fy everywhere along the member. That doesn't happen here. Like right here, we'll hit the ultimate tensile stress right there, but over here the stresses will still be a little bit lower. Not the entirety of the cross section can be effective in transferring stresses. And so what we do is whenever we're looking at the net section, we have to take the capacity and we have to reduce it some. We have to reduce it some by this factor called U, which represents shear lag. And shear lag is just shorthand for this phenomenon that we're talking about. It's like the idea is like if you have an angle and one leg is bolted but the other isn't, and you yank it, this leg is seeing stress, but this one isn't, so it sort of like lags behind. So that's where the term shear lag comes from. Now the idea is we are not going to perform some rigorous computational finite element analysis for every single tension member that we design. What we would like to do is use what's called an empirical expression. You all have already been using empirical expressions in a lot of your classes. And by empirical expressions, I mean engineering equations that aren't exact, that will approximate what's going on. I imagine some of you in maybe some of like Dr. Waite's hydraulics classes probably have some empirical expressions for friction factors and stuff like that. Like the physical phenomenon is really complicated, but you need something that you can use that will get you an answer close enough to where you can size the pi for, in this case, size the tension member. Same idea, right? And so what we're going to talk about on Monday are these shear lag factors and how to use different ones, and there's little nuances associated with them, how they apply. There are multiple cases that can apply to a single problem and how you deal with that. What I'll tell you is that this is on table D3.1. It's in the back of the manual near the gray section. If you're borrowing a manual from a friend, chances are they already tabbed this page. This would be a good bookmarking page in the manual. 16.1-34. It's right there in Chapter D. I would tab it because you will reference it not only on your homework, but in our first celebration of learning. Okay? I don't want to steal my own thunder on Monday, and I'm feeling generous. I'm going to give you 8 minutes of your life back. I'm going to stop the recording, pull up the QR code one more time. Y'all have a wonderful weekend, everybody. I'll see you on Monday.